We orbit around a star as part of the solar system. This star is one of 100 to 400 million stars that make up the Milky Way. Our solar system is unique in many ways, and one of those is that it only comprises one star. Most star systems actually consist of two stars called a binary system. Most binary systems can be hard to detect. The easiest way is through visual observations where it is possible to resolve the individual stars themselves. This is most often not possible, so astronomers have to rely on other techniques. One involves looking at changes in the spectra of the starlight, which can show a wobble to the motion of the star, indicating that it is moving about a common center. The third method uses a measurement of the light intensity received by the star. Many stars show a periodic change in their apparent brightness. This could happen for a number of reasons. Some stars undergo changes in their intrinsic luminosity. The other possibility is that it is a binary system where the orbital plane lies edge-on to us, so that the stars periodically eclipse one another. These systems are called eclipsing binaries. Sometimes these systems can contain more than two stars. But now NASA has detected a new and bizarre sextuple system in which all the stars are aligned perfectly, creating a sextuple eclipsing star system. More strange is that the system seems to consist of three pairs of binary stars locked into an exotic dance. It was discovered using NASA's Exoplanet Hunting Transition Exoplanet Survey Satellite, or TESS for short. TESS is cataloguing how the brightness of around 800 million stars change over time. This means that they can identify stars whose brightness dips, which is usually a good sign that a planet might be in orbit around the star. Using this mechanism, they were able to identify 100 star systems with potentially 3 or more stars. From this data, they were able to identify the rather remarkable sextuple system TYC 7037891. So let's examine the system in a little more detail. They can identify 3 pairs of star, pair A, B and C. When we examine the masses and the size of the stars in the system, something rather remarkable stands out. Each pair of stars consists of one larger star, which is brighter, and one smaller star, which is smaller. It also appears as if the ratio between the larger and smaller star is consistently the same throughout the system. The estimated temperatures of the stars are also consistently the same for both the larger and the smaller star. Pair A orbits each other every 1.3 days, and pair C every 1.6 days. Pair A orbits pair C every 4 years. Much further out from pair A and C sits pair B. These orbit each other every 8.2 days. And B orbits pair A and C every 2,000 years. This system is a very interesting find, and the astronomers offer no clue as to how such a system could form. Although the idea of star capture is possible, the sheer number of binary star systems rules out this possibility as the main cause. Instead, mainstream scientists rely on the idea that some fragmentation of the molecular cloud occurred, causing multiple stars to be formed. The problem here is that this has to occur 3 times at different locations, but every time in the same ratio split of 2 to 1, and also with the plane exactly aligned to Earth. In the electric universe, there is a much simpler way of looking at these systems, so let's break this down in a different way. We know that stars form along filaments, and that plasma flows along these filaments. As the plasma flows, it will tend to form into filaments. One large flowing mass of plasma will form into a number of smaller filaments. As the currents flow along these filaments, they will generate a magnetic field which will cause the filaments to become attracted to each other. This often results in the formation of twin filaments wrapping around each other. Peratt studied these in detail in his laboratory and has written about them in his book on the plasma universe. Of particular interest is a computer simulation he performed, which showed that when 3 filaments start to form, and 2 are slightly closer to each other, then this attractive force will cause the 2 closest to wrap around each other, and not the other one. This may be an alternative way of explaining why stars form and are often found in pairs. And in this example we would have the initial formation process whereby 3 stars formed. two much closer due to the attraction, and one on a much larger orbit compared to the others. When Peratt looked at the interactions of Birkeland currents, he saw that when the filaments pinch, a double layer forms at the same point in each filament. This would also therefore explain why all the stars are in the same plane with their rotation vectors aligned. So how would we explain a sextuple star system then? In the electric universe, the stars are powered by the movement of this plasma. Stars will form where a filament becomes pinched, causing the material to be compressed in a small area. Electric stars attempt to balance their incoming current and electron availability with the output brightness and surface area. Sudden dramatic changes to the incoming current density can cause an overload to the star. The only way to deal with this increase of charge is to create a greater surface area. The simplest way to do this is by splitting the star in two. This immediately increases the surface area greatly. These events are often referred to as electrical stressing events, and the splitting process is called the fissioning of the star, meaning it splits into two. We also suspect that stars can become ejected from their birthing filament. This is something that I have previously looked into if you are interested in more details on this. The basic concept is that the filaments are not stationary, so while the star forms and is small, it is able to move with this moving filament, but at a certain point it gains enough mass that it can no longer follow the movement and gets kicked out of it. As the stars formed at the same time, it is likely that this process happened at the same time for all three stars. Upon leaving the filament, it is likely that the stars would have undergone a significant electrical stressing event, causing them to fission. This would have resulted in the formation of a close companion to each of the initial three stars. This would not only explain how it is possible to create a sextuple star system all aligned along the same plane, why they all have pairs of stars where one is about a third the size of the other, and why one of the pairs is so much further out compared to the other two pairs. There is one other possibility to explaining this sextuple star system. It is important to remember that they are not able to resolve the differences between the pairs of stars in each system. So is it possible that what they see as variability in luminosity is not caused by an eclipsing star at all, but instead is caused by the flickering of the star itself? We know that our Sun undergoes a regular change to its output, but this is on the order of years, not days. What we do see is that all three star pairs seem to have a very similar variation in their brightness, which is assumed to be caused by one star passing in front of the other. Is it possible that all three stars are connected somewhere to the same source of electrical power, and that the circuit has a similar resonant frequency for all of them? Until we are able to resolve the differences between each pair of stars, it is not possible to know which of these two scenarios is the more likely to have occurred. These types of unusual, almost miraculous star systems are slowly building a picture of how stars might evolve, not just singly, but as pairs, or in this case up to 6 stars, and shows that the interaction of the Birkeland currents together is an important aspect that must be considered.